Hello, my name is Demitra Selimos, and I'm excited to share my summer research about the effect of fasting-induced metabolites on cerebral blood flow and how this impacts astrocyte calcium signaling. Here is a brief overview of what I will be discussing in my presentation. My project was inspired by mounting evidence about the robust beneficial effects of fasting on numerous aspects of health, ranging from Alzheimer's disease to cardiovascular disease to even diabetes. However, despite this new research, the mechanisms for these beneficial effects are not well characterized. It is believed that changes in cerebral blood flow may act as a key mechanism for these benefits, especially in neurodegenerative diseases where blood flow is impaired. Recently, it was discovered that during fasting, the microbiome secretes a metabolite called indole-3-propanoic acid. IPA is known to influence the cardiovascular system, yet its effects on the brain's blood supply have yet to be studied. Therefore, we attempted to make a novel connection between two different body systems, the microbiome and the brain. Also, during fasting, the liver secretes a ketone body called beta-hydroxybutyrate, which alongside indole-3-propanoic acid are able to pass through the blood-brain barrier. Together, these metabolites nourish glial cells such as astrocytes, which modulate cerebral blood flow alongside neurons. This project included two main aims. First, we wanted to determine if IPA and beta-hydroxybutyrate induced vascular changes, and whether these changes resulted in vasodilation or vasoconstriction. Next, we looked at astrocyte signaling to see if astrocytes were releasing or taking in calcium after being bathed in either metabolite. Calcium is a necessary secondary messenger for the signaling cascades needed to change vascular tone. So how was this done? First, I took a transgenic mouse that was engineered to express green fluorescent calcium in astrocytes only and performed a retroorbital injection. By injecting a fluorescent arterial marker, I was able to label all vessels in the brain green. Acute brain slices were then prepared using a vibratome, which slices the brain into really thin pieces, and these slices were incubated in artificial cerebral spinal fluid, and then in a red dye, which labeled all the astrocyte somas red. The slices were then imaged using 2-photon fluorescent microscopy in the following manner. First, the slices were incubated with U46, which is a vasoconstrictor, to give the vessels tone and mimic physiological conditions. Next, to stimulate fasting, the slices were incubated in either metabolite. To analyze my data, I used the tool on ImageJ to track arterial diameter and area changes during administration of the metabolites. As you can see, after IPA administration, there is a trend toward increased arterial area. To determine statistical significance, a paired t-test was conducted for each slice from a time point at its baseline to its peak effect. For IPA, most slices showed a significant increase in both of these parameters. What you're seeing here is an arterial marker in cyan and astrocytes labeled in magenta. Between baseline and peak IPA administration, there is a pronounced increase in both area and diameter. However, qualitatively, there was no consistent trend with astrocyte calcium signaling. For beta-hydroxybutyrate, there was also a trend toward vasodilation, with each slice showing a significant increase in arterial area and diameter from baseline to its peak effect. Here's another image showing vasodilation between peak and baseline, this time with beta-hydroxybutyrate. There is yet again a significant increase in vessel diameter and area. Beta-hydroxybutyrate did demonstrate clear astrocyte calcium dynamics as the frequency of calcium events per second decreased after metabolite administration. Particularly, astrocyte end feet, which are the processes that wrap around the endothelial vessels, showed a drop in intensity after administration of beta-hydroxybutyrate. This can be more clearly visualized through a video of the actual astrocyte calcium signaling. What you're looking at here is the vessel, astrocytes, as well as in cyan, you're seeing the astrocyte calcium. At the beginning, prior to administration of beta-hydroxybutyrate, there are a lot of microdomain firing events, particularly at the end feet. However, after administration of beta-hydroxybutyrate, the signal starts to quiet globally, and you can also see a drop in that signal at the end feet. In conclusion, indole-3-propanoic acid and beta-hydroxybutyrate caused arterial vasodilation and modulated astrocyte calcium dynamics to promote increased cerebral blood flow. In the future, both metabolites should be compared in control and Alzheimer's disease mice to determine their impact on arterial dilation and calcium signaling in both a healthy versus a neurodegenerative brain.
I would like to thank my supervisor, Dr. Grant Gordon, and the O'Brien Center for the Bachelor of Health Science for funding my summer studentship. Thank you for watching.